Hey guys, Spency's back. Now let us discuss the last part of the second long exam, which are multiple unit balances. Well, to be honest, there is not much change with our multiple unit balances from the first long exam. However, we must explore more advanced conversion concepts. Since we are dealing with multiple unit balances, we need to clarify some more conversion concepts, which include the single pass conversion, which is the conversion of the limiting reactant within the boundaries of the reactor, and the overall conversion, which is a conversion of the limiting reactant within the boundaries of the system. Now let us use these concepts with this simple problem. Given the reaction and diagram below, let us determine the different conversions. Please note that we have a recycle stream in the diagram which aims to maximize the potential of a reactor since it is less likely that the reactor will proceed to completion. Now for a single pass conversion, it is basically 70 minus 50 all over 70, which are the values that enter and exit the reactor. Our overall conversion, however, is 50 minus 30 all over 50, which are values entering and exiting the system. Thus, the single pass conversion as calculated is 28.57%, while our overall conversion is 40%, which indicates that the recycle stream increases the conversion of our reactants. Now, this is more or less the only concept we need to utilize for our multiple unit balances with reactions, so let us use these concepts in a chemical engineering problem. After perfecting his fermentation techniques, Ethan decided to build an alcoholic drink manufacturing plant. However, he was unable to get the recipe when this problem was created. He only went as far as creating the 8% volume by volume solution, in which he also made a calculation error such that it is volume alcohol over volume of water. Glucose and water enter a hydration chamber in which the glucose is dissolved. The two substances exit towards the reactor, wherein yeast at 100 kilograms per second is used as a catalyst. After producing carbon dioxide and ethanol, all substances enter a separator, which separates the 8% alcoholic mixture, and the rest is recycled back to the reactor. Around 2/5 of the recycled stream, which consists of 17.036% yeast, 63.884% water, and 7.155% ethanol, is purged to prevent outflow. If the yearly target of the plant is 21,286.8 megaliters, determine the single pass and overall conversion of the reactor and the mass flow rate of the glucose and water streams in the hydration chamber. Now let us go back to our calculation chamber and let us continue to solve this problem as we all did before. Hello guys, welcome back to the calculation chamber wherein we're going to solve that chemical engineering multiple unit problem with reactions. Now, as good chemical engineering students, let's first start solving this problem by creating a diagram. So I'm just going to draw a diagram here. So we have mass of the glucose entering a hydration chamber with the mass of the H2O here. Both of them come out as MF. And the reactor is here. This is the reactor. The mass of the carbon dioxide comes out. But then again, all the rest comes out here. So that's MP. Yeast comes in here at 100 kilogram per second. This is the mass of the yeast. Then we have a separator. We have a separator which separates the 8% of alcoholic drink, which is required to be produced at 58.32 megaliters per day. I've already did the conversion rather. And we have here the recycle stream, which is purged with a composition of 17.036% yeast, 63.884% H2O, 7.155% ethanol, and 11.925% of glucose. Now, after doing this, we are going to decipher on what the reaction is. So the balanced chemical reaction is C6H12O6 produces 2CO2 plus 2CH3CH2OH. Now, we know that in this setup, we have two non-reacting species, namely the yeast and the water. So let's do our calculations with a basis of 1 second. We could do 1 day, but again, 1 day will give us lots and lots of big numbers, so it's better if we're just going to use 1 second. So if we're going to have a basis of 1 second, we have to convert this into per second. So that's 58.32 megaliters per day produces 675 liters per second. All we have to do here is we have to divide this by 24 hours and divide it again by 360 seconds. Then we got 675 liters per day, which could be summarized into 625 over 18 kmol of H2O, since it is 8% by volume. And we have 50 divided by 46 kilomoles of ethanol. Now, in this system, we know that yeast is like a non-reacting species, just like water. So we have one source of yeast for this entire system. We have one source of yeast for this system, which is the 100 kilograms per second. And we know that in this system, there's only one outlet of yeast, which is the purge stream. So we know that this is 100 kilograms per second. This must also be 100 kilograms per second for the yeast. So we're just going to write it here, mx equal to 100 kilograms of yeast. Then we could use this value to get the value for other components. So that's that's 375 kilograms of H2O, 42 kilograms of ethanol, and 70 kilograms of glucose. Now, since this is a physical separator, and we have the compositions of this, and we know that the purge stream is just 2/5 of the entire stream, we could now get the composition of this stream. And since this is just a physical separator, we could now get the composition of MP. Now, we're just going to do that later, but first we're going to get the values for MF. Now, if we're going to rely on this kind of balance, we could do a reaction balance for MF, MA, and MX. So let's just continue to do that. So for the composition of MF, we know that MF only consists of water and C6H12O6. So, and water is a non-reacting species. So the amount of water here in MF is just equal to the amount of water here and the amount of water here. So the amount of water here is approximately 625 kilograms. Then the amount of water here is 375 kilograms H2O, which is equal to 1,000 kilograms. Now we know that the mass of water going into this system is equal to its source, which is the mass of H2O here. So from this analysis, we could now get the mass flow rate of water, which is 1,000 kilograms per second. So this is the mass flow rate for H2O. So that's one down. Next, we are going to balance the glucose. So now our glucose enters here, then exits here and here. However, we all remember that glucose is a reactant, so we have to also accommodate ethanol in this part. So we know that in order to produce 2-ethanol, we need a single molecule of glucose. So let us first combine the ethanol in here and in here. So we have 50 If it would be alright, I'm going to use molecular species balance for this problem. So we know that there is 50 divided by 46 kilomole of ethanol in the alcohol stream, and in the purge stream we have 42 over 46 kilomole of ethanol, which gives us approximately 50 plus 42, 92 over 46 kilomole of ethanol. So now we're going to use our equation. This is your out. Our in is basically 0 plus the modification term. Our modification term here in this instance is 92 over 46. So modification term for ethanol is equal to 92 over 46. And remember that our modification term for ethanol is just 1/2 of the modification term for glucose. So that's divided by 2. So after which, we just divide this by 2 to get the modification term for ethanol. So thus we get for 92 divided by 46 times 2, which is 1. So our modification term for glucose is equal. Sorry, this is not equal to 1. This should be times 2. Is 4. So we're just going to do that. So our modification term for glucose is 4. And let's just use the equation here again and get the outlets for glucose. So we have 70 kilograms of glucose here. There's no glucose going out here, so technically the only glucose here is the 70 kilograms here. And now the molar mass of glucose is 6 times 12 plus 12 plus 6 times 16 is 180. So we have to divide by 180. Is equal to here. Oh, sorry, I'm just going to write it here as MF of glucose because it's only one outlet plus 4. Minus 4. Sorry, this is supposed to be negative. So it's minus 4 here. So what we're going to get is 70 divided by 180 plus 4. We have 79 over 18. Thus, MFG is equal to 79 over 18 kilomole. So after which we can now get the mass flow rate of oh wait, no, sorry guys. I am completely mistaken. This is supposed to be MTE times 2 is equal to MTG. So technically, the one that we got earlier, this is supposed to be 1, and this is supposed to be minus 1. Sorry, this is negative. Since this is a reactant, this is a product, so they have different signs. So this is now negative 1. So MFG minus 1, we get not 79, but rather 25 kilomole. Here. Converting that to mass balance, we now have 250 kilograms per second. This is your mass flow rate for your glucose. Because remember, the glucose here will just go here. And all the glucose here is just derived from here. Now, we're up to our bigger challenge, which is determining the single pass and overall pass of the limiting reactant, which is, well, technically there's only one reactant, so we'll just use glucose. So we have 25 over 18. We're going to use an overall conversion first because it's much easier that way. So this is our out. This is our in. and our 70 over 180 is our out. So I'll just plug that in. We have 25 divided by 18 over 25 divided by 18 minus 70 divided by 180. We get 72% conversion. So our overall conversion is 72%. Now, how do we get a single pass conversion? Please note that in the single pass conversion, we're considering this and this stream and this stream. Unlike in the overall conversion where we only consider this stream and this stream. So now we have to consider this stream, and this stream. So in order to get the composition of this stream, we just have to get the composition of this stream, and we have to multiply it by 3 divided by 5. So in order to get the glucose of this stream, we just get the glucose here, which is 70 kilograms. So 70 kilograms of glucose, we divide it by 2 divided by 5, which is equal to 70 divided by 2 divided by 5, which is 175. Now, this amount of glucose is equal to the amount of glucose, the amount of glucose here is equal to the amount of glucose in this stream, which is equal to the amount of glucose in this stream, since this is just a separator and this stream has no glucose in it. So technically, the glucose in here is equal to the glucose in here. So that's 175 kilograms, which is basically our out. Now, the glucose in the recycle stream, we just multiply this by 3/5. So multiply by 3 divided by 5, we get 105. So our mg in is equal to this amount, which is the amount of glucose in the F stream, 25 divided by 18 plus 105 over 180, which is approximately, so we divide this by 180 plus 25 divided by 18, we get 71 over 36. And this is approximately 175 over 180 kilomole. So using such, let's get a single pass conversion, which is 71 divided by 36 divided by 71 over 36. Then we just get minus 175 over 180. We're going to get 50.704%. So that 0.004%. So this is our single pass conversion, and this is our overall conversion, and these are the mass flow rates of the streams earlier. So yeah, we just solved a multiple unit balance problem. That is it for our second long exam coverage. Hi everyone, it's Spency from ChE. If you want to subscribe to our channel, please make sure to subscribe using the logo above. And if you want to check out more ChE 101 videos, you could check out our videos using the video down below. Thank you for watching, guys!